So in the last lecture we learned about the perceptron model, and specifically we learned about the forward pass in the perceptron model. Let's do a quick recap before we move on to the backward pass of the perceptron. So in the forward pass we saw that we have all these inputs and we have these weights. We calculate the weighted sum of all these inputs. So basically we multiply all these inputs with their respective weights, calculate their sum, and then pass it along to an activation function. This activation function is non-linear, so it adds non-linearity to it. We explored various activation functions like tanh, sigmoid and ReLU, and we get a predicted value of y. Now that was the forward pass. That is how that is the operation that our neural network uses to calculate the predicted value. But how do we train the model? So what training basically means is there is this output value y hat, okay, which is the predicted value, and there is the reality in our training data set. So reality is the actual value of y. Now the whole goal of training is to adjust all these weights such that all these weights and bias such that our predicted value gets as close as y here, or the reality. Now to do this we have to first find out that how off we are from the reality, right? So we need to find out how much do we need to adjust these weights such that whatever output we get after this operation of the forward pass is closer to the reality, which is the value of y. So what we do is we need to quantify the difference between these two, or the we can call it error between these two, and we do that by using a function called the loss function, which is denoted by the capital letter L here. Now these loss function depends on the task that you are trying to perform. Okay, so in machine learning there are basically like two tasks. There is also clustering and other things, but we'll focus on these two things as of now. So there are regression tasks and there are classification tasks. So what happens in regression is that you want to predict a continuous numerical value. What we need to do here in regression is, for example, we want to calculate the housing price based on the area, the location and all those things. So that because price, you see, will be a continuous value, right? So or let's say based on the experience and job profile, you want to identify the salary of a person. All those things fall into the regression category. And then we have the classification problems, where we want to classify the inputs into different classes, or we want to find out discrete values. For example, when we talked about the iris data set, there the motive was to divide the input or predict it into different classes, 3 of the classes. Now for each of these tasks we have their designated loss functions that we need to use. So for regression tasks, the most commonly used loss function is the mean squared error. So in mean squared error, what we try to do is we take the value of y hat and we subtract it via the value of y, and we can know that, okay, if you see in this graph, this point here is greater than the point here on the predicted value, right? But at the same time you see that this point here is smaller, the real point here is smaller than the predicted point. So what we try to do is we square the resultant value so that it is always positive and the penalty on error is high. Yeah, so similarly, for the classification problems, we have cross entropy loss. Whenever we have two discrete classes, we use binary cross entropy. And whenever we have more than two discrete classes, we use something called the categorical cross entropy. Now, what entropy basically means is the uncertainty in some kind of data set. So, the formula for entropy is something like entropy is equals to minus the summation of probability multiplied by the log of that probability. Okay, but here what we are trying to calculate is the cross entropy. So we are trying to calculate the cross entropy between the actual value versus the predicted value. So in classification, what happens is we use something like a softmax, and if there are only two discrete values, we use something like a sigmoid function at the final layer, so that as I mentioned earlier in the softmax as well, that it can represent probabilities, right? So it represents the probability of a certain class for a certain input variable. We can consider it like that. So that is why we use this cross entropy loss here for any kind of classification problem. Okay, so that was all about the error functions. Now, since now we have quantified our loss here through these error functions or loss functions, what we can proceed to do is identify how we can train our model such that they are lower. So for any individual set of inputs, so for example, here you have all these input sets, right? Here as well you have all these input sets. For any one set, when you calculate the value, it is called loss. But when you find out the average of all those losses, it is called the cost function. So it is just a difference of notation here. The cost function is just the average of all the loss functions. So here you can see from I starting from 1 to n. So starting from 1 to as many number of data points we have. What we try to do is we calculate the loss function and then find out its average. So we divide by the total number of those points. So we calculate the average of that loss functions, and that gives us the cost function. And the whole aim of our training is to find a set of weights that minimize this cost function. Okay, we do not really train over individual points one by one. Why? Because that will kind of increase the overfitting in the model. So it will like try to fit the model for each of these points. But also we do not want to increase train for all these points at a time. So instead what we try to do is we try to train the model in batches. So when we try to train our model in batches, what happens is it does not get overfitted because of the cost function of all those set of points, and it is also kind of a little faster than training on individual points, and it gives better results overall. So here the argument function basically means the set of weights where this cost function is minimum. So cost function can be represented like this here, and we know that okay, what this y hat is. So we substituted the value of y hat here. So y hat here is basically a function of x, which are the input parameters, and the w, which is the weight. Now how do we do it is through this algorithm. This algorithm is called the gradient descent algorithm. So let's talk about gradient descent. In gradient descent, if you remember your 11th and 12th grade calculus, there as well we had to find maxima and minima, right? And for that we used derivatives. Now, why do we use derivatives for such cases where we have to find the maxima or minima? It is because derivatives tells us the rate of change of some value when we change some other value by a little bit. So here our goal is to find out how much the cost function changes if we change the weight a little. So that is what the derivative tells us. But here we are not using the derivative, actually we are using gradient. They are almost similar, but there is a small difference between it. So gradients are kind of the partial derivatives of something. So what does partial derivative mean? You see that here the cost function is actually a function of x and the weight, right? So there are individual weights here that come in. So when you expand this further, what this will be like, the loss function of x1 w1 x and y1, and similarly x2 w2 and y2, and you keep adding them forward. So you can actually predict how much individual weight contributes to the loss. So each of these weights you can calculate how much they contribute to the loss, and when you find out derivative with respect to each of these individual weight of the loss function, it is called the partial derivative, and that is what we calculate here. Why? Because we need to update all those individual weights, right? So we let's talk about the algorithm first, and then we'll talk about this intuition. So in gradient descent, you first initialize the parameters or the weights randomly or heuristically, and then what we do is we do a forward pass. We calculate the value of y hat, and then we compare it with y, calculate this loss function, and we do this for our batch. Okay, we do this for our batch. Let's say we take a batch of 8 values. So we calculate the average or the cost function of all those 8 values. That will give us the average loss. So we are not overfitting it to any particular value. And then what we do is, based on that derivative of the cost, we multiply learning rate, small learning rate, and we subtract that product from the original weight. Now this value that we get by subtracting the product of learning rate and the gradient of the loss function with respect to the weight, we get the new value of the weight. Now we keep doing this, we keep updating our weight like this until we converge. So what does convergence means? Convergence means that we have reached the local minima, or we have reached somewhere closer to the local minima. We never really reach the exact local minima ever, because that would mean that we have, so if your loss is very low, it kind of means that you have overfitted to your data as well. So for example, converging to 0 would mean that the line would be something like this. So it will trace the training data itself, and it won't generalize well. So we try to minimize it up to a certain level, and that's what gradient descent means. So we do this for a certain number of epochs. We run this a certain times, and we see that, okay, if our loss is decreasing, yeah, it means that we are converging. Now why do we subtract the value of the gradient multiplied by some learning rate? It is in the name here, right? So we are trying to descend to the minima of the function. That is why we try to subtract. So it is very intuitive. If you see, if the gradient is negative, which means that if we increase the weight, the loss function would decrease. So that is why we multiply with the minus sign here. So the negative gradient becomes positive and we add on to the weight. Similarly, if the gradient is positive, which means that increasing the weight would kind of increase the loss function as well. So we subtract the weight here. So in that way we decrease the weight a little bit. That is why gradient descent works. So we subtract the gradients little by little and we converge to the local minima. Now this here, this thing, repeating this loop iteratively by finding the gradients with respect to different parameters for the loss function and updating the weights accordingly, is called backpropagation. Now let's explore this and let's relate it with chain rule as well in the next slide. Yeah, so here I have taken example of mean squared error to demonstrate how we calculate gradient. And I've taken this screenshot from machine learning with PyTorch and scikit-learn book by Sebastian Raschka. So so this is the derivative of the mean squared error, and here it is the y subtracted by the predicted value of y. And how do we calculate this derivative? So this is where chain rule comes in. So first we take the constant out, so which is 1 upon n, and now when we derive this we implement chain rule. How do we do that? So this here can be considered as some value u. Now think of this derivation as derivation of u squared. Okay, this here is u, so find the derivation of u squared. You take out the summation as well, and then the derivation of u squared will be 2u, so you write 2u here. Now what we have calculated here is dy or d of l by du. Now we will calculate du by dw. That is the chain rule, right? So chain rule basically means if there is a function u of v of x, then what we do first is we do du by dv, and then we do dv by dx when we have to find the du by dx. So that is what we are doing here. We are first finding the derivative of this whole thing here, which is 2 multiplied by this whole thing, and then we are finding the derivative of this thing here. And similarly we calculate the derivative of rest of this value, and finally what we get is minus 2 by n, the summation of actual y subtracted by the activation function multiplied by the predicted value of y multiplied by the x. Now there is a problem with the perceptron, which is that it can only work for linearly separable data. So this is the problem that also caused what is called the first AI winter. So initially there was the golden age of deep learning when the perceptron was discovered, and it was able to fit into most of the logical functions like the and, or, not all those functions. But when it came to the XOR problem, it failed miserably because of the nature of this problem. You see, this data is not linearly separable, and we discussed it in one of the most earlier slides as well. When the data is not linearly separable, you need that is why we needed activation function for creating the non-linear decision boundary. Now we do have activation functions here, but if you see, even the activation functions only can separate linear values. So here if you see, it can create the hyperbolic tangent can create the separation between the top part here and the minus part here. So for whatever value, if we get a value less than 0, it can be class 0. If we get value like more than 0, it can be class 1. Similarly for here, the linear separation comes at 0.5. So similarly for ReLU as well, it is a linear function. But as I mentioned, that what we do when we build real neural networks, we kind of create layers of them. So when we create layers of them, all these things, they kind of superimpose upon each other, and like we take these small units and join them together into something complex such that it fits into a non-linear data set, and that is where multi-layer perceptrons come into the picture. So in multi-layer perceptrons, each of these nodes are individual perceptrons. So individual these things, these units are present in each of these nodes, and we stack them together however we want, and we create a multi-layered perceptron, and each of these nodes is connected via some kind of weights to all the inputs. So you see all the inputs here are connected to all of these networks. So the number of weights here would be, so the number of weights here would be 4 multiplied by 3, which is 12, plus 3, which is 15, and then 3 is a 9 plus 3, which is 12, 27 plus 3 is 30, and 1, 31. So all of these arrows are the weights, and all of these nodes contain some bias as well, which is also a trainable parameter, and similarly the same goes for here. And then we have the output. This is not actually a weight, this is just me returning the output here. Why? And all these layers in between are called the hidden layers in a perceptron, and since these are all fully connected, so each of the input is connected to each of the output, it is called a fully connected layer. Now this is very interesting, and we will try to implement this in the next video. But all of these things that we have learned before, so the gradient descent works the similar way for the multi-layer layered perceptron as well. For each of these weights, we calculate the gradient with gradient of the loss function with respect to each of these individual weights, and we use chain rule for calculating it based on the prior thing. So that's it for this video. In the next video, we'll try to implement multi-layered perceptron as well as the single unit or the perceptron model. Thank you.